are in, oops, don't know what that is, generalized linear models with examples in R. We're in chapter 3, question 318, and this has apparently 12 parts. So we're going to be looking at a data set that is measuring body fat percentage and BMI of adults between ages 23 and 61, and it's called human fat. So we won't read all of these parts of the question. We'll just kind of come to them as we come to them. So the first thing we need to do is to install the GLM's data package, which I've already done, and call it up. And then we need to load human fat, and I'm just calling it D, and we'll get a look at its structure with the str command here. Okay. So we have a data frame with just 18 observations, 4 variables, and they are listed right here. Okay. So part 1, so we're going to plot the data distinguishing between males and females. Which assumptions of linear regression, that is, appear to be violated. Okay. So I'm going to plot this, and I'm just, to distinguish males and females, I'm going to have females as red, males as blue. Okay, so I'm doing that with this if-else command. And I'm also giving them different markers here. It doesn't matter too much, but we'll run this. And so here we have it. Okay, so we have males in these blue triangles here, and then women in the hollow red circles. So as far as violations of assumptions of linear regression, I would suspect that there is probably some heterogeneity of the variance, right? So it looks pretty variable right here and less so up here. So that would be one thing that's being violated here. Okay. So part 2 is fit the linear regression. Okay, so fit linear regression model with the systematic component being percent fat being regressed on age and gender in the data. Okay, so I'm just calling this M. So I have percent fat regressed on age by gender. And then I have the summary right here. And we won't look at this right now, but we will come back to the output here in other parts of the question. But that's how we would run this. Okay. So now we are going to write down the systematic components, this part, for males and females according to the output of mSum. You know what? I'm actually going to display the summary here, so you can kind of see what's happening here. Okay. So we're going to have so we're going to write so we're basically going to write this part here for males versus females. Okay. So ignore here the age seek part because I'm just putting that in here so I can plot these two different lines, and we'll get to that in a second. So we're just going to look you know, here and here. Okay. So so let's try to make this linear component, systematic component, for the females. Okay. So if I come up here and I look at how R has kind of encoded my model. Females are going to have an intercept for sure. Okay, so that's the first coefficient of M summary. They're going to have an age component, right? So that's my second coefficient, right? And that's why I'm multiplying that by age seek here. Okay, so we can plot them. But now for gender, so it has encoded males as 1 and females as 0, right? So I could have the third coefficient in here, which would refer to gender male, but I would just be multiplying it by 0 because because R has encoded as a dummy variable and assigned 1 to males, 0 to females. So I can just omit it. And same for the age by gender interaction. Okay. So then for males, okay, so for males, I want to bring in the gender coefficients. So it's going to be exactly the same as for females, but plus these other two coefficients here. And so I'm just going to use for females, I'm going to use that template, okay, plus the male coefficient, okay, there and there. All right, so that's what's happening in that code there. So I can run that, and this is not the best plot that we will make here, okay, but we're showing roughly the systematic components for males and females. Okay, so female being red, males being blue. All right. So now we're supposed to interpret each coefficient for the model here. Okay, so I guess maybe I'll show M sum here again. All right, so let's do that. So so the intercept is the body fat percentage for females, right? Because so the intercept is the value of percent fat when all the other variables are set to 0. So when we set gender to 0, we get females. We have age of 0, and we have so in that condition, then percent fat is 20 plus or minus 6 roughly. Okay, that's the estimate. Okay, and this estimate has a p-value of what it has. All right. Now there's some interesting consequences here that are just consequences of regression, and that is absurdity when we go beyond what is in the data, right? When we extrapolate beyond what we see in the data. Now there's a few ways that we can push absurdity here. Okay, so if we take age to be 0 to correspond to the moment of birth, okay, well then it may make sense. Like you have a newborn baby, it may make sense that its body fat percentage is this. I mean, I don't know, but I mean, it's possible, okay, that is a good estimate, all right? But then notice what the p-value is doing, right? The p-value is saying, well, what is the probability that it's actually 0, that the estimate is actually 0? Well, if it's a newborn baby, even though we say that the probability for the intercept is greater than 0, right? So there's a greater than 0% chance that this newborn baby has no body fat. We actually know that there's no probability that a newborn baby has 0% body fat. All right. So that's interesting. Now, if we start counting, so if instead of counting at age equals 0, we start counting at conception. So now you just have a fertilized zygote, I think it is. So now I don't know that it makes sense to say that there is any body fat on the zygote, right? That seems like a nonsensical statement, okay? And maybe we want to say that percent fat is 0 in this case. I'm not really sure. It seems like the lipids of the cell membrane could count as technically fat. I'm not really sure, but let's just say that it doesn't. Well, now we know that percent fat is 0 with 100% probability. Okay, so these absurd conclusions that I'm making are a consequence of extrapolating beyond the data. That's all I'm saying here. Okay, so now let's move on to the age coefficient. Okay, so this basically says that as age increases by 1 unit, which I assume here is in years, that there is an increase in body fat percentage. How much? Well, 0.24%, body fat percentage plus or minus 0.12. All right. And so this increase is regardless of sex, of gender, okay? And this happens at a p-value of 0.06. So in other words, there is a decent probability that, or how do I want to say this? There's a 6% chance that the actual value is 0 according to this estimate. Now, we can kind of start to uncover more absurdities a little bit here. So it may just be a law that body fat increases with age, regardless of gender, and I think maybe we could make a pretty strong argument for that. In which case, we may say that this p-value is much less likely to be 0 than the p-value that we have found here. Okay. So anyway. All right, so now we're on to the next one, gender for males here. So this means that males have less body fat than females, okay, at a p-value of this. How much less body fat? Well, just by virtue of being male, on average, you have, 29.3% less body fat plus or minus 10 here. Okay, that's what that's saying. And now finally, the age by gender says that in addition to the effect of age on body fat, males have an additional factor here that is increasing their body fat above and beyond females as they age by 0.6 body fat percentage points. Okay, again with such a p-value. All right. Okay, now part 5, we're going to use a t-test to determine if the interaction being the age by gender term, to determine if the interaction term is significant. Okay. So first of all, so we're actually gonna, we're gonna look at the test here in a second. But if we just come back up to the figure that we made, even though this is not a very detailed figure, there is some evidence here for an interaction. Why is there an evidence for an interaction? Because the males and females have different slopes, right, to their regression line. So that would be evidence of an interaction. If there was no interaction, then the two lines would run parallel to one another. Okay. So we're actually going to manually find or conduct a t-test here. But notice that that with the LM function, it actually runs the t-test for us for each of these terms here. So we get a t-value of 1.9, and that has a corresponding p-value of 0.0679. All right. So that's fine, but let's do this manually. So our t-statistic would look like this, right? So we have our estimate for that coefficient, okay, for the interaction coefficient, minus the null value, which here is 0, divided by the standard error of the term. Okay, so I'll make my t-statistic here. Okay, so I've just encoded all of this. Okay, so that will give us a t-value. Okay, right here, which matches what we found with the summary function. And now, if I want the p-value, I use the pt function for apply it to t beta, and my degrees of freedom are the number of observations minus the number of parameters, which is 4 here. Okay. Now I'm multiplying it by 2 because presumably we're doing a two-sided test. Okay. So what does PT do? It gives you the cumulative probability distribution. So I won't go into showing how that maps onto the p-value and everything, but hopefully you're familiar with that. This is just how we do it in code. So we get this p-value right here, which again matches what we found with the summary function. All right. Okay. So now in part 6, we're instead going to use an F-test to determine this. All right. So one very simple thing that we can do here is recognize that the t-statistic, no, how do I want to say this? The F-statistic is the t-statistic squared. Okay. So if I just take t beta squared, okay, I will get my F-statistic. In fact, maybe I'll show the F-statistic here. And then we again want to find the cumulative probability of the F distribution. Okay. So again, I use the PF function, and then I need to figure out what the degrees of freedom are for the F-stat. And so now when I run this, so I get my F-statistic here and the corresponding p-value. What is the corresponding p-value? Well, it's identical to what we already found. Okay. The other thing that we could do is to just run ANOVA, or the command ANOVA, over the model. Right. So when I do that, here's my F-statistic, which we already found here, as well as my p-value, which I found here. Okay. Oh, I forgot to mention up here, how we're finding the degrees of freedom. The 2 degrees of freedom. Okay. So one of them is the number of parameters, I guess, that we're testing here, and then the other one is is how many residual observations that we have, or in other words, the number of observations minus number of parameters being estimated. Okay. Okay, so now in part 7, we are to show that the p-values for the t-test and f-tests are the same for the interaction term, explain why, and also show that the square of the t-statistic is the f-statistic. And we've already done that, so I just say see above here. All right. Part 8, so now we're going to plot the separate regression lines for males and females. Okay, so we kind of did this above, but I'm just going to make a better looking plot here. And you can look at the code and emulate it for yourself or make whatever modifications that you want. But we have males in blue, females in red here. And we have, I believe this is a 95% confidence interval. I'm not sure what I set it to here. 90%. Oh yeah, the question actually wants 90%, I think. So, so I've set this to a 90% confidence interval. Or somewhere it wants a 90% confidence interval. So that's what I've set it to here. Okay. I don't think there's really much more to say about this. So I'll just let you look at the code for yourselves. Okay. Oh, here we go. Compute and plot the 90% confidence intervals. That's why I use 90%. About the fitted values for males and females and comment. Okay, so we did all that. So I don't really know what to say about it other than, there's quite a bit of overlap. So. Okay, part 10, argue that it would be sensible to use only females in the study, and further, that it would be also defensible to use only females over the age of 38. Okay. Now let me say a couple of things here. I'm not sure that it actually is sensible to use only females or only females over the age of 38. That would really depend on, what you believed about body fat percentage in males and females, if they really differed or not. If you didn't believe a priori that they differed, then maybe it would make sense just to use females. And the reason is because one, when we consider both males and females, there does seem to be this discrepancy in the assumptions of linear regression, namely, this largely heterogeneous variance. Okay, so that would be one problem. And so that's complemented by the fact that all but 4 data points are female, and so we wouldn't be throwing out that much data. Okay. Now, why above 38? Well, I mean, similarly, because the heterogeneity really comes from these very young people that were in this study, and so if we just go to 38, we still get the bulk of the observations here. Okay. So in part 11, we're going to use that proposed subset of data, females over 38, to predict percent fat. And we're going to use age and BMI. So here's the model. So I'm calling it M sub, I guess, for subset of data. Okay, so we have that. And to explore this, instead of looking at the coefficients, I'm just plotting it. Okay, so this is what we have. So I have all of the data, but now just the regression line based on the data that was used in the observation. Okay, and so that's what we get. It's pretty similar to just the red line that we got above. All right. So now, using the model that we just looked at, compute the Cook's distances, the leverages, the studentized and standardized residuals to evaluate the model, identify any outliers, influential observations, and discuss the difference between the studentized and standardized residuals. Okay, so let's do some things here. So first, I'm just calling the plot function and applying it to that model, and that gives me these figures right here, which we've seen several times. That kind of give us a at a glance understanding of how well the model is fitting the data. Okay, but we're actually supposed to compute particular values. Okay, so here I'm computing the Cook's distance, the leverages, the studentized, and the standardized residuals. I'm going to jump ahead a little bit and comment on the difference between studentized and standardized residuals. Okay, so the major difference is that the studentized residuals, how do I want to say this? The studentized residual for any particular observation is how far away that observation is after having omitted that observation from the fit of the model. I hope that makes sense. The standardized residuals don't do that. They take the distance of each observation from what is predicted to be after using all of the data to fit the model. Okay, so yeah, so in that sense, the standardized residuals are how do I want to say this? If you have an observation that is an error in recording, is an obvious outlier for whatever reason, maybe the measurement was bad or something like that. The standardized residuals, it is calculating that residual based on having used that observation to fit the model. And so, the extent of the depravity of that particular observation is not going to be fully represented because that observation is influencing the fit of the model. For studentized residuals, though, that is not the case because that deviant observation has been omitted when assessing its residual. Okay, so I hope that makes sense. So so we can we could go through and look at all of these guys right here numerically, but I've just generated a plot with this code right here, and so these things are not necessarily on the same scale, right? Cook's distance is not necessarily on the same scale as, say, studentized residuals, but they're close enough to where we can just kind of put them all in the same plot here. Okay, so for Cook's distance, I've found I've estimated a value above which we're saying that that Cook's distance is high enough that I want to label that an influential point. Okay. Similarly for leverages, I have done some back of the envelope calculations, and you can look at them in the code and agree or disagree with them, but found leverages to find high leverage points, so if they're above this red line. And then for quote-unquote outliers, I've used studentized residuals above 2. Okay, so yeah, so we see that we have one outlier. We could also have it below 2, but there weren't any observations that low, so it's not plotted. All right. Okay, this has been a long one, but I think that is it.